Welcome to section 3.4. In this unit box, there's really nothing new, nothing you need to know except for one thing. In the imperial system, sometimes mass and weight are confused. Weight isn't going to be given in pounds. If you want to use the formulas in this section, you're going to need to convert pounds to mass, and the mass in the imperial system is a slug. So you're going to divide by 32. For most of your career, your mathematical career, probably since high school, you've been assuming that when an object falls, the only force acting on that object is acceleration due to gravity. And that's an okay model. And that gives you this equation here. And you can see that position is independent of mass. And that's because if we start with force is mass times acceleration, the masses cancel. And back in about 350 BC, Aristotle thought that heavier objects actually fell faster than lighter objects. And then flash forward to Galileo dropping objects off the Leaning Tower of Pisa, he was able to show that no, heavier objects don't fall faster than lighter objects. They fall at the same rate. But enter air resistance. We know that air resistance can be important. Remember the raindrops? If we don't factor in air resistance, raindrops would be falling at 400 miles an hour. So in this model today, we're going to assume two forces are acting on our object. One, acceleration due to gravity. That's m times g. And two, the force due to air resistance. And that's going to be proportional to the velocity. So kv, or actually your book uses bv for some positive b. And that's actually a pretty good model. The air resistance is proportional to velocity. The only time that breaks down is when you've got really high velocity. So for example, rockets are more like air resistance is proportional to velocity squared. But for your pedestrian everyday problems, this is a good model. So now we've got mass times acceleration is the force due to gravity plus the force due to air resistance. Now this equation is going to take on one of two forms right here, depending on whether the origin is in the sky or you place the origin on the ground. I'll tell you which equation to use when I want you to use it, so you don't really have to memorize those. All right, so I'm going to do an example of each one with you today. We've got a stork that drops off a 400-pound baby from rest at 500 feet above ground, and we're going to let the origin be where the stork drops the baby from in the sky. Force due to air resistance gives us B equal 10. And the book will phrase that as the air resistance force is negative 10V. That's a little confusing with the sign, so I just say B equals 10. Step one, write down a differential equation for dv dt in standard form and state the initial conditions. So standard form is dv dt plus P of t v equals Q of t. All right, and so we're using this differential equation because the origin's in the sky. Gravity's working with us. M is 400 pounds divided by 32. So I've taken pounds divided by 32 in order to get slugs. B is 10 and G is 32. Since I'm using the imperial system, acceleration due to gravity is 32 feet per second squared. So now it's just a matter of plug and play. So I went ahead and started this for us because there's no reason for you to see me do arithmetic. I put in 2 over 25 for M into this equation. I put in B is 10. And I put in G is 32. Then I multiplied both sides by 2 over 25 and put it in the correct format. dv dt plus P of TV is Q of t. And so now the only thing left to do in part one is state the initial conditions. V of 0 is, okay, the baby's dropped from rest. That's code for V of 0 is 0. And then, comma, X of 0. X is going to be the position. X of 0 is 0 because we're letting the origin be where the baby's dropped from. Okay, so 2, solve for V of t. The reason why I want to put this into standard form is because I'm going to find an integrating factor. Mu is e to the integral of P of t. P of t is 4/5 dt, which is e to the 4/5 t. So now I've got the equation mu v, so e to the 4/5 t v is the integral of mu q. So q is 32, so 32 e to the 4/5 t dt. And so we integrate, so that gives us 40 e to the 4/5 t plus c. and then divide both sides by mu to get v equals 40 plus ce to the negative 4/5 t. Use v of 0 equals 0, and if we put a 0 in for v and a 0 in for t, we're going to get c is negative 40. Right, so we've got v of t is 40 minus 40 e to the negative 4/5 t. All right, and that's all we had to do in part 2. Part 3 is solve for x of t. Okay, x is position. Position is the integral of velocity. And it's a straight up integration because v of t only depends on t, so we don't have to do any fancy solving of differential equations here. We just do a straight up integration. We're going to integrate 40 minus 40 e to the negative 4/5 t dt to get 40t, then plus 50 e to the negative 4/5 t plus c. Now we're going to find c by using x of 0 equals 0. So if I put 0 in here, then I get 50 plus c. So c is negative 50. Okay, so now I have x of t equals 40t plus 50 e to the negative 4/5 t minus 50. Part 4 is approximately when does the baby hit the ground? Ignore the exponential term. So for part 4, remember the origin's up here in the sky. This is here. So here's the baby being dropped. This is 0. And so it's going down. It's going to hit when x is 500 because it's dropped from 500 feet above the ground. So we're going to set 500 equal to x and solve for t. Now, here's where you're going to either need technology or use the fact that you can ignore, in this case, the exponential term. This actually, when you solve this for t, you're going to find that the value of t, for which this is true, makes this term absolutely tiny. So we're going to set that equal to 0 and get t equal to approximately 550 over 40. And that's 13.75 seconds. And then finally, part 5 is, the question is it a soft landing? How fast is the baby going when it hits the ground? Well, it hits at 13.75 seconds. And so if we want to know how fast it's going, we want v of 13.75, and that's about 40 miles per hour. And that's not a soft landing. It hits pretty hard. Let me show you some shortcuts on Desmos. Here's the stork problem. Desmos doesn't like it if you use x as your function name. So I named my height h, but since I have another h below, in a problem below, I had already used h, so I had to name this h sub s. So h sub s is my height, and we found if we ignored the exponential term that h was 500 when t was about, 13.75 seconds. Another way to do it would be type in h, so give yourself a function name, and then write down the function y equals 500. That's going to be a horizontal line. That's the green line. H is the red line. So those meet the intersection here. Desmos knows when you want an intersection at 13.75 seconds, which is exactly what we got. 13.75. All right. And then another shortcut, I typed in v, the velocity function. Let's say you don't have a calculator with you. Just type in v. You can call it v as long as you don't have a v below, but I called it v sub s. And then I said, okay, Desmos, compute v of 13.75 for me. It gives me 39.999. That's where I got the approximately 40 miles per hour. All right, so you don't need Desmos to do this. You could use a graphing calculator, but I think Desmos makes it kind of easy and fun. All right, let's go back to our lecture notes. At the end of the lecture notes, I do this problem again, but I show you, I do it with the perspective that the origin is on the ground. So I use a negative here, and I change up the initial conditions. Now, if the origin's on the ground, x of 0 is 0, and I show you get the exact same answers. So changing the location of the origin, as long as you're consistent with your initial conditions, isn't going to change your answers. The one thing that does change is that the velocity when it hits is negative 40 miles per hour because it's coming down and up is the positive direction. All right, so let's do one more where the origin is on the ground. All right, so now we're using m dv dt is negative mg minus bv. And we're using the metric system, so we don't have to worry about mass units. 2 kilogram Hostess Ho-Ho is shot upwards at 200 meters per second. The force due to air resistance is B is 1 over 20. And so we're going to pretty much go through the similar steps as we did before, write down a differential equation in standard form and state the initial conditions. So my M is 2, my B is 1 over 20, and my G is 9.81. All right, I just plug those numbers into this differential equation, and then putting it into standard form, I want to divide both sides by 2, and I get dv dt plus 1 over 40v is negative 9.81. So that's standard form. And my initial conditions are v of 0 is shot upward at 200 meters per second. So v of 0 is 200, and x of 0 is 0. Now we're going to solve for v and for x. So step 2, solving for v, I'm going to need an integrating factor. So mu, I'll just jump to the answer, is e to the 1 over 40t. We can do that integration in our heads. And so that gives us the equation to solve, that e to the 1 over 40t times v is the integral of negative 9.81 e to the 1 over 40t dt. This is negative 392.4 e to the 1 over 40t plus c. Little note on decimals, I did not round that. That's the actual value, 392.4. If, let's say, so your homework asks for final answers to 2 decimals. And the rule is, if you want 2 decimals in your final answer, then for your intermediate calculations, you carry twice that many decimals. So if there were 4 decimals here to carry, I would be carrying 4 decimals. All right, and so now divide both sides by mu to get v equals negative 392.4 plus c e to the negative 1 over 40t, and use v of 0 is 200 to solve for c. Get 200 equals negative 392.4 plus c. So c is 592.4. So our v of t is negative 392.4 plus 592.4 e to the negative 1 over 40t. That's my v, and my x of t is the integral of that. So the integral of v of t is negative 392.4 plus 592.4 e to the negative 1 over 40t dt, which is negative 392.4 times t, and then it's going to be minus 23,696. Again, I didn't round. There were just no decimals here. So e to the negative 1 over 40 t plus c. Okay, and now we're going to use x of 0 is 0. So I'm going to get c equals, I'm just going to do a mental calculation, positive 23,696. So our x of t is negative 392.4 minus 23,696 e to the negative 1 over 40t plus 23,696. Okay, that's the boring stuff. Part 2 and 3, when does the ho-ho turn around? How high does it go? So for when the ho-ho turns around, the ho-ho goes up, the velocity is positive, and it comes down, the velocity is negative. Up here, that's when the velocity is 0. So to find out when it turns around, we're going to set v of t equal to 0. Now, one way to do this would be to graph v of t on Desmos. So write a function v of t equals this up here, and then see where it crosses the origin. And that'll give you v of t equals 0. But this is actually easy enough to solve by hand. 0 is negative 392.4 plus 592.4 e to the negative 1 over 40t. So that gives me e to the negative 1 over 40t is 392.4 over 592.4. Take the natural log of both sides, negative 1 over 40t is ln of 392.4 over 592.4. And then finally, multiply both sides by -40, and we get t is -40 ln of 392.4 over 592.4. Now you do need a calculator. That's approximately 16.48 seconds. I rounded, it was 16.47 something. So let me show you that on Desmos. Here I've got the ho-ho problem. Okay, here's V, and V of t is 0 at about 16.48 seconds. We can also just see where V crosses the t-axis, and we get 16.476 seconds. I got 16.48 seconds, so yeah, that's about right. Then I went ahead and I typed in h of t for position, and I typed in the position function that we found. We called it x before, and then I wanted to know the last question, which I haven't done yet, is how high does the ho-ho go? Well, we know it turns around at 16.48 seconds, so if we compute the height at 16.476 seconds without rounding, we get 1,534.81 feet. So you can use, again, using Desmos as a calculator. So type in h and then compute h at the value you want. Let me go back to part 4. How high does it go? We want x of the value we got before. And if you're being careful, you would do x of 16.476 instead, because you don't want to round to the end to reduce your rounding error. But I think in either case, you get pretty much the same thing. You get 1534.81, and this would be meters. All right, that's the end of this section.